again. So I'm going to talk for about 15 minutes, and we'll finish this, our first Twedit exercise. And maybe, but I think it would be good if everybody can follow me. I mean, if I do whatever I'm doing on the screen, try doing the same on your machine, okay? So this will be a good prelude to Giuliano's presentation. So he will be teaching you how to build a vascular tumor. So this will be extended session, and I think it would be good if you at least can build simple simulations. So I'm going to open up Twedit again. So my and if you open Twedit, go to CC3D project, and first menu, new CC3D project. And I'm going to call it demo, and you do the same. All right? Hit next. On the next screen, also hit next. If I'm going too fast, please stop me.
So my screen actually.
Oh yeah. This is fine. Yeah, you're on Mac. Yeah.
Yeah, Mac has a slightly different.
Exactly. Yeah. So they do things a little bit differently. And the reason for that is that this framework, it's called Qt or Qt, depending how you pronounce it, is a cross-platform framework which works everywhere, and they try to emulate the native behavior of every system. So even going from Windows 7 to Windows 10, this dialog will look completely different, and the buttons will be in different places. I'm not going to show and bore you with the details, but this is completely normal. So we're hitting next or continue. We're going to add cell types. You know, for the sake of let's call it cell A, add, and cell B. Right? Hit next. If you want to add diffusion solver, that's fine. But maybe, maybe let's not add diffusion solver this time. Let's just hit next on the chemical fields. And now I want to add contact and volume local flex constraints, and hit next. Contact and volume local flex. And don't do anything else. And finish. So you should get in your left-hand panel this tab called demo.cc3d. If you double-click, all the files that belong to that project should open. Let's inspect. Let's start with XML. Let's actually move this height. Let me do that. So we have our pod section. You remember 256 by 256. This was in the wizard, and other numbers were also in the wizard. So now it's your opportunity to change it, right? If you think that 100,000 Monte Carlo steps is too much, let's change it to 1,000, whatever you feel like, and hit save. So after each model, well, make sure to hit save. I'm going to save it now. So save is Apple S or Control S on Windows. So this is pod section, which determines basic properties of simulation. Now, then you have cell type. So cell type is essentially a list that associate your cell type name. And remember, we had two cell type names, cell A and cell B, right? Think of it mesenchymal or endothelial cells, right? I just, for simplicity, I picked cell A, cell B as types. Medium cell is this, so lattice is square lattice. So whatever pixels are not covered by cells, they are called medium.
Not because
Yes. So now I'm not sure. I believe I have to reshare screen. It's really annoying that. All right. So there's medium cell, and what else do we have? We have center of mass plugin, then we have contact plugin. So we have tracking of center of mass. Then there is volume plugin. So volume plugin is essentially volume constraint, right? And Juliana will talk more about that. And then we have this uniform initializer. So uniform initializer essentially creates a quadratic block of cells in the lattice. That's all it does. So let's run it. So how do I run it? Well, I run it like this. I'm going to open new terminal. And I'm going to go to where my simulation is, Compusol is installed. 2, 3. I'm going to open player. Now, I'm going to open the simulation. Now I have to go to the CC3D project. So now you have to be careful. You have to find where your simulation is. I don't know. You might have stored it in different places. But I think mine are in directory called Workshop 2019 and Demo. That's my simulation. I'm going to open it. And as usual, first thing I usually do when I start new simulation, I hit step. I don't hit play. I just hit step. Because I want to see if first, initialization of the simulation proceeds correctly. And it looks like it does. So here's the lesson. 20 seconds with Twedit generates you functioning simulation. This simulation doesn't do anything interesting now, but it's a skeleton for you moving forward. So instead of you spending an hour and fixing all the typos in the editor, well, here's your time saver. Now, let's look at the output. I hit the step button, and I get all these printouts. Cell ID 12. Where does it come from? So this is now your investigative work. Let's take a minute and try to locate where this comes from. So there are 3 files in the simulation. 3 files in the simulation. Demo, XML, demo PY, and demo steppables. Take a minute and try to locate where this printout, this ugly printout, cell ID comes from. I mean, there are many ways to look at this. You can read the files, that's fine, or you can simply search for this, cell.id. So I'm gonna actually maybe, I don't know, I'm not gonna be searching for this because I know where it is. So it's not in XML, because XML doesn't do those type of stuff. It's not in this file because this file doesn't have any print statements. The only print statements that I see is in the steppable file. And this is the line. So here's the thing. When Twedit generates a steppable for you, and steppable is, I have to explain. Steppable is, it's a module that runs every Monte Carlo step or every 10 Monte Carlo steps, right? So the way it goes, you perturb cell lattice, and then you run Python steppable. And Python steppable is a short script that changes cell properties, right? So this is where this thing is coming from. If we comment it out, so let's try commenting this out. So you highlight stuff, and then you, I don't know, is this block comment here. All right, so this is what was interesting. So by commenting those 2 lines, we got rid of this ugly output. Another interesting thing is that our cells are disappearing. We get tons of cells. Let me show you again. So this is our step 0. tons of cells, 500 cells. And I'm gonna click through that. Maybe I will just hit play. And you see that those cells are disappearing, right? So why are cells disappearing? What is wrong? I can tell you what's wrong. Cells, in order to exist with positive contact energies, and I know it sounds cryptic, need to have volume constraint. So you need to have volume constraint on a cell. So you need to have an energy term that will tell if you deviate too much in either way from your target volume, you will get penalized. And the way you enable this energy term in CompuCell is by specifying that, by declaring that you're going to use volume energy term here. But now, there are no parameters here. We don't know what target volume is. So that means that each cell has individual target volume and lambda volume. And is everybody familiar with the spring constant, spring energy? So, you know, I'm not sure if I have presentations here from last year, but this is where I think this is what we will need. Essentially, you have quadratic penalty. So you say that volume of the cell has to be 25, right? And the energy term that penalizes will be actual volume of the cell minus 25 squared. So if you deviate from either way, if you go below 25 or above 25, you will have positive energy penalty. And the goal in CompuCell is to minimize energy. So you want energy to be minimum, to be minimized, right? So you don't want any energy terms with positive contributions to energy term. So that means that cells should have as close volume to the target volume as possible. So how do we program it? Well, we go to start function. So start function, so first of all, this steppable is being called every Monte Carlo step. And there are two other functions, start and finish. Start function is going to be called before any Monte Carlo step takes place. So all the cells are on the lattice, everything is initialized, but now you have this is your option to do some extra initialization. So what I'm going to do, I'm going to teach you here. How do I iterate over all cells? Well, you can copy this line from that we commented before, or you can go to CC3D Python, visit menu, and say all cells. If I hit this code gets right. So that's the code that got pasted in. So again, let me show you. I'm going to remove this code. So I want to paste this code in the start function. So I'm going to the start function. I put my cursor somewhere, and I go to CC3D Python. I go to visit, because we'll be visiting all cells. And I'm going to set visit all cells. And it will insert code snippet that's essentially a starting point for your code. So now instead of printing, well, first of all, what we can do, we can run the simulation and see what happens here. So let me start and run the simulation. Stop it and run the simulation. I'm going to hit start button. So now observe the output. Previously we had only cell ID, right? Now we have ID, type, and volume. As an interesting modification, we can add surface, right? Why don't we add surface? Does it make sense? So surface equals cell dot cell surface. So that's what I did, right? Sorry. That's the code I typed. After self.volume, I type in quotes, surface equals, comma, cell surface. So this is typical print statement. I'm gonna save it. I'm gonna go back to my player. I'm gonna stop previous simulation because each time you modify Python, you have to stop simulation, right? And that's normal. If your Python code is running and you modify it while the code is running, your changes have no effect, right? Because what Python does, first thing what Python does, it first translates Python code into bytecode executable, and it executes this bytecode executable, right? It doesn't look anymore at your input. So if you want your changes to be, reflected in the code, you have to stop the simulation. I stop the simulation. I'm gonna hit start again. And I'm gonna go to the console. And now I have my surface printout. Does it make sense? So that's interesting. The volume has 49 pixels, or right. So we have, so essentially volume measures how many voxels or pixels a given cell has. So this tells me that this volume, if the volume is 49, that means that cell has 49 pixels. But why is the surface 0? The surface is 0 because in order for surface to be non-zero, you have to explicitly request tracking of the surface. By default, we only track volume. And this has to do with efficiency reasons. And that's how it is. So if you don't request surface tracking, you won't see surface being displayed. Now, but we are talking about printouts. Now we want to change actual volume constraint, and we want to prevent cells from disappearing. Because if you run, you can see that cells are disappearing. I'm going to do how to do it. Instead of printing out, I'm going to comment out the code. I'm going to type this, cell dot equals 25.0 cell dot equals 2.0. So target volume is the target volume of the cell. How big the cell should be. Actually, you know what? I'm going to make it 50. I'm going to make it 50. Because I've noticed that my cells originally had 49 pixels, so I don't want to be shrinking them. I want them to be. And again, if you don't know where this is coming from, this lambda volume and target volume, well, you can look at the examples, or you can look at cell attributes. And cell attributes will tell you, for example, what type of attributes you have. You have target surface, right? So I inserted it. You don't have to do this. I'm just showing you where in Twedit you would find cell attributes. Or you have lambda, where is lambda volume? Lambda volume, right? So that's where you can get exact capitalization for those variables. So let's get rid of this. And now, let's save the script. Let's save the script. And let's run simulation. Yes, I will. Absolutely. Sorry. So it's for cell in self cell underscore list. And run it. So the nice thing here is that we are at step 300, and as you remember, there were no cells, almost no cells at that step. Right now, everything is there. Does it make sense? Has everybody been able to follow that simple exercise? So now I wanted to ask you to do something. I know what I want to ask you. Oh, I know what I want to ask you. Okay, so now that you know how to set target volume and lambda volume, how would you implement growth? So let's say I want cells to grow to increase their volume every Monte Carlo step. How would you do it and where? So I want cells to gradually grow. So obviously, in this step, obvious, take 2 minutes and see if you can grow cells. And what would you do for cells? What would it take for cells to grow? Yeah. So try writing it on your own.
Every time how you hold the system is by making, so this lives in a pixel grid, and every time you make those pixels and you flip from one pixel identity to the next pixel identity, okay? So this, of course, will make the cell change shape, but because there is a energy term that the cells have some kind of energy with the boundary of all other objects, this positive energy tends to erase the cell, because the algorithm of CompCell is by having an energy function that guides the behavior of the cells, and the algorithm tries to minimize this function. Okay, so to prevent the cells from being wiped out from simulation, we add this kind of Hamiltonian term here, which is called the volume constraint. And all kind of energy terms in CompCell behave more or less like this. So here in this energy term, so H is just a, in cellular pots model, we call the energy term the Hamiltonian, and this is the volume part of the Hamiltonian. So this is the energy. And the energy is, you loop over all the cells, so this is all the cells in your simulation. And here you compute what's the volume of the cell. So this is going to be the exact number of pixels that the cell has. And here is a value that you set up in the simulation called the target volume of the cell. How many pixels the cell would like to have. Yes. Yes.
So my question is this for both A and B, or how do I say that A grows B?
You can set up for one cell type and for the other cell type. You can even set up for each one of these two cells.
Yes. So essentially, that could be another exercise, right?
Yeah.
Have different growth rates for different cell types.
Yes.
Or different lambdas. You can, by changing lambda, you can make cells stiffer.
Yes.
Right? Because it will be very hard to deviate. If your lambda is 1,000, it will be almost impossible for cells to deviate from target volume. If your lambda is 0, then there is no constraint. So, you know, we can play with that.
So before that, we have this term being equal to 0, effectively, also this term, so this didn't have. But right now, every time you flip a pixel in your random pixel flipping in the algorithm, you also always compare what's the current volume that I'll gain and what's the against the target volume. If this pixel flip diminish this difference, then you're minimizing the energy. So all the pixel flips that move this value closer to this value will be minimizing the energy. Okay. And of course, this is modeled as a spring. So that's the kind of spring term that you have, because it's some kind of constant times the difference which you are trying to minimize is squared. Why squared? Because you want a deviation that is either up or below it to be penalized. So if you make the graph of how the Hamiltonian varies with the actual volume of the cell, let's say that this is the target volume. So, and this is 0, so the energy will have a quadratic term. So any deviation, so if you have a volume of the cell that's actually bigger, it gets penalized. And if it's smaller, it also gets penalized because this has goes with the different volumes squared. Okay. And then the actual value of this depends on this lambda that you have here. The pressure will be the derivative of this. So, yeah.
Derivative of that, right?
What?
Pressure? Yeah.
What? It's Hooke's law. So that's the spring term. Yes. So,
Yes.
yes.
So actually, this is a very good point.
Yes.
So actually people like Luigi Preziosi and Marco Sciana from Italy, from Torino, they actually edit. They have a paper and they use computer and they edit those fancy energy terms that took into account, different behaviors, like shrinking and expansion. So, and their potentials are not symmetric. Yeah, yeah.
Mm-hmm.
So we don't have this code. I mean, we can get it, but their paper is fairly well. I mean, it's like 50 pages of scientific writing, fairly accessible, so you can get it. And they describe how they tackle those problems.
And again, I think we should probably move on to Giuliano's demo. But there's a simple comment here, which is the goal of this function is to keep the actual volume close to the target volume. If you're in a situation where there's a great deviation between the actual target volume, then you're probably misusing the method if you're trying to represent cells, because cells really are incompressible. They have a high hydrostatic pressure, a high osmotic pressure. And so the actual volume of the cell is always quite close to its target volume, its real target volume. Now, if you're trying to simulate an ideal gas in a balloon, then, of course, you can have large compression. And so in those situations, thinking about a more elaborate potential is reasonable. But we know, if there's a restoring force in both directions, the lowest order approximation is always going to be a parabolic. And so fundamentally, this is simply saying that there's a restoring force.
All right.
So you'll see that again and again where you'll use an elastic restoring force. That doesn't mean that in any particular case you actually really have an elastic restoring force. But I'd say 99% of the time, the errors you're making from that are smaller than the other simplifications you're making, which is not always. There are times when it's significant. But this particular one, it tends not to be the case. If you go into extreme situations, you can in fact squeeze cells out of existence. And that's telling you that fundamentally you've picked a parameter set that isn't appropriate for the simulation. You'll run into that, actually. Giuliano will talk about this, that there are certain things you have to check by hand to make sure that you're in a physically meaningful region of the parameter space. And so your example is a good one. If you were under enormous compression, then this wouldn't make sense. Biologically, if you wind up in that situation, you have to think about it. But in general, we're not. Because generally, biological tissues aren't under extreme pressure. But it's a very good point. As a physicist, you want to think about this.
All right. So essentially, this is what I did. I asked you to figure out the way to grow cells, and you probably did it. I'm going to just show you how it runs. And so now my cells should be growing. I'm not sure if they are growing. They are growing. You can see that, right? So at every Monte Carlo step, I'm increasing cell target volume by 0.01 pixel. So, you know, you don't want to be increasing or perturbing simulation parameters too rapidly, right? You want to do it in adiabatic fashion. So be gentle with, you know, growth rates and all other stuff. Now, if you want to, I can write a code like this. If cell type equals cell A, then do this. And then I will write a code like, hold on, this is out of whack. L if cell, actually no, else will suffice. Like this. Minus. So some cells will start growing, some cells will start shrinking, and I will do one more thing. If cell gets volume less than 0, I'll write this. So essentially what I'm doing here, I'm just trying to prevent target volume to becoming negative. So each time after my cell target volume goes below 0, and I detect it, I just reset it back to 0. And you know, there are many other ways to do this. I'm just showing you the most straightforward way. So I'm going to run this simulation. I'm going to switch back to editor in a second, okay? So that you can copy it. But let's see if the simulation works at all. This is it's the same simulation. So as you can see, certain cells are dying. Yeah, green cells died, and the blue ones, well, they won. Because the blue ones always win. Not always, but. Oh, and one thing, you know, in the player, I'm not sure if I showed you how to change colors. You can always, I think, change colors of cells. So you can make the blue ones, I don't know, red ones, or I don't know what color it is. Not sure if this will, yeah, it works. Right, so if you want to change color, you go to configuration, cell colors, and you know, you can play, pick something reasonable. I think this is okay for now. What did I do? This is crazy. Oh, I changed window color. Window color should be this one. Yeah, back to normal. All right, so let's go. I'm going to show this stuff. Now, if you ever, I'm sure you are puzzled what I typed here. Why didn't I type equals 1? That's perfectly fine. You can do that, but you can also do that. Sorry. So this is how it works. You look at your XML, and you see that your cell type 1, the cell with type ID 1, has type name cell A. If you capitalize all the letters here, and you type self, sorry, if you type self.cell A, all capital letters, this will get resolved as 1. And the reason why it's useful, because, you know, keeping track of, you know, 1s, 2s, and 34s is kind of confusing. But this, you know, you know cell A, what cell A and cell B means in the context of your simulation. So I think I'm going to stop now.